you are free to do otherwise. Okay. Thank you, Greg.
Thank you, Nicola. Yes, so as Nicola was saying, I just finished my PhD in mathematics and now doing a postdoc in physics. And so I feel a bit like a Monty Python character showing up here with something completely different. And obviously the kind of primary question I think we're all looking at, hold on, the slides aren't changing, there we go, is the question of free will. Are we free agents or are we controlled by some other power? I like this comic, and some of us might be facing this kind of scary shock when we reach heaven one day and perhaps find out that we've been controlled by a puppet master all along. And this is the question kind of primarily that I'm considering, but I'm going to be looking at this from a mathematical perspective. So to begin with, I'm going to be just discussing briefly what is a mathematical model. I think the easiest way to think about a mathematical model is a set of assumptions or presuppositions written out using mathematics. So how this usually works in practice is that there might be a neuroscientist or a biologist or a psychologist who has some understanding of how some cognitive process works. They write that understanding down either themselves in mathematical terms or just in words, and a mathematician comes along and is interested and writes a mathematical description of this, usually in the form of a set of equations. And the mathematician might make extra assumptions that are mathematical assumptions to make things simple, solvable, but those don't necessarily change the basic understanding that's being tested in the model. These models are then investigated using either just purely mathematical techniques or simulations to see whether that understanding holds up under some kind of mathematical investigation. So the context of my talk then, and I'm going to run through this a little bit briefly just to kind of put where I'm coming from into a little bit of perspective. So there are many physical experiments, thought experiments, and theological or philosophical reflections that enlighten our understanding of consciousness and free will. Mathematical models are tools used by neuroscientists, psychologists, and artificial intelligence researchers in order to test, develop, and expand our understanding of free will and consciousness. And this has become increasingly dominant over the last 30 or so years, especially with the development of artificial intelligence that can do things like speech recognition or reproduction, image recognition, things like this. Each mathematical model comes with its own set of assumptions. Some of these are purely mathematical, like I said. Those usually just help the mathematician actually be able to get something useful out of the model, because if they were pure reflections of reality, that'd be far too complicated. But most of the main assumptions reflect a kind of a priori, at least from the modeling perspective, presuppositions about the cognitive process. And when I say a priori here, I don't mean that there hasn't been a physical examination of some experimental data. I mean that the model itself hasn't been observed. No one's run simulations of it, no one studied it from a mathematical perspective. And so when the model is built, the assumptions go in and then it's investigated. And that determines the bounds of both the input of the model and the output of the model. What I'm going to be looking at in this talk is primarily this last point. What assumptions do each type of mathematical model make, and how do they accommodate free will or consciousness? How do they relate to our philosophical or psychological understandings of these types of things? So I'm going to be going through a number of different types of mathematical models. Obviously, given the time parameters, I don't have time to go into many of them in depth, although I probably will spend a bit more time on the sorts of models that I was working on in my thesis. Okay, so the first type of model, which is really a kind of more general category of model, is this idea of the computational theory of mind. That is to say that the brain is a computer and that the mind is just something that comes from the brain. And so the whole thing can be understood as a computer. This picture I have on my screen is a Turing machine. So this is a very simple type of computer. The basic idea is that you have this piece of paper, and in theory, it's of infinite length. So you can encode as much information as you want on it. And the machine does one of four things. Either it prints a symbol, it deletes a symbol, it moves one position to the left, or it moves one position to the right. And Turing kind of postulated that these types of computers could compute almost anything. And so far, he's been proved to be right. So the types of computers that we use, the silicon chips, can be shown to be equivalent to a Turing machine like this, where you're basically changing one symbol at a time, moving up and down one space at a time, either printing a symbol or deleting a symbol. And this includes things like artificial intelligence. They can also be described as Turing machines. And so this very simple mechanism of printing a symbol or deleting a symbol as you move up and down the tape as a way of encoding information has shown to be an incredibly powerful tool. And a few of the next models kind of fall into this type of category, where people who believe in the philosophy of the computational theory of the mind believe that your brain is basically a Turing machine, or can be compared to a Turing machine. The first type of model, and probably the most common type of model used, is called a network model. In the picture here, I have a little picture of the brain showing a whole bunch of neurons connected to each other, or maybe not neurons, but something small, connected to each other in a network shape. To kind of justify this type of model, see where it's coming from, this is a picture that I actually had in my thesis. These are measurements of a rat busy tasting different things. So they're measuring the gustatory cortex, just the activity of the neurons there. And in these three rows, so firstly in the columns, we have the rat tasting sugar in the left, quinine in the second column, citric acid in the third column, and salt in the last column. The bottom row shows 10 neurons being measured, so 1 to 10. And so we see that, for example, when the rat tastes sugar, at first you see neuron 3 busy activating and firing, and a little bit of neuron 1. That kind of fires for some time, and then there's this kind of rapid switch to a new firing pattern, which is given by, I've lost the mouse, oopsie, which is given by the state number 2, where a few more neurons are firing, and then you see state number 3, where different neurons are firing, and so on. And so these 10 neurons being measured in the rat's gustatory cortex show these kinds of firing patterns. In the top row, you just see which pattern is active of the 10 neurons firing. So for about a third of a second, the first firing pattern is active, then the second firing pattern is active, then for almost a full second, the third firing pattern is active, and then the fourth, and so on for each of these different flavors. This middle row just shows the same experiment being done for 4 different rats. So it's the same plot as the top one, but for 4 different rats. And what you see is that there's certainly differences in how long each rat is tasting a certain component, let's say. But by and large, the pattern remains the same for all 4 rats. They all taste, their firing patterns follow a particular sequence. And so we can model this as a network in one of 2 ways. The first way is to take the 10 neurons at the bottom and connect them to each other. This would be a kind of very biologically motivated way of conceiving of this, where you actually have neurons connected to each other by axons and dendrites. As one activates, it will send a spike to another one, and the energy gets transferred through the system. And that kind of would be this bottom picture here. We've got these 10 neurons all connected to each other. Another way to create a network model of this is to consider each of these states, these collections of firing patterns, as one unit. And then you only have, for example, in the case of sugar, you'll only have these 4 states. And they seem to go in order 1, 2, 3, 4, and then if you keep feeding the rat sugar, it will repeat. Here you see it go 1, 2, 3, 4, 3. And so maybe it go 1, 2, 3, 4, 3, and whatever. And so you get a network not of neurons, but of activation areas or regions. Perhaps MRI images or EEG images in a sequence. And this was the focus of my thesis, was looking at models of these kinds of brain states. Although my thesis was very focused on the mathematics, not so much on the psychology. These types of models buy a lot into this idea of the connectome or the dynome, that is the highly structured manner of the brain. The brain is structured both by neurons being connected to each other, but also networks of neurons being connected as networks. You can think of suburbs being connected by highways or cul-de-sacs, where one little subnetwork has its own kind of role or function, and then it might send a large amount of information to another network within the brain. So a question then is, what happens when neurons in a network like this interact? In this picture, I have a model result. So the time series shown on the right is showing the activation levels, not of real neurons, but of mathematically modeled neurons. In this case, these are modeled using the Hodgkin-Huxley equations. And there's pretty much one or two equations that people mostly use to model neurons. The other one being Fukuyama equations. And in this system, we have 3 neurons. So neuron beta is shown at the bottom row, neuron gamma in the middle, and neuron alpha at the top. And we see that neuron beta fires, we have a spike, basically meaning that the neuron has received enough information that it's decided it's going to send information to all the downstream neurons, or send energy to the downstream neurons. That causes neuron gamma to have a spike, and that causes neuron alpha to have a spike. And so you see the sequence of spikes. So coming back to the kind of underlying assumptions on this type of model. And to me, the most relevant one is that this is almost an encoded, mathematically encoded version of Lebet's experiment. So Benjamin Lebet, I actually don't know when this was, quite a few decades ago, did an experiment where he asked people to freely move their fingers and then measure their brain activity. And they had to record when they chose to move their finger by basically moving their finger. And what was interesting about the results of this experiment was that when the person decided to move their finger was not when the brain activity started. The brain activity actually started before the person had a subjective experience of choosing to do something, which made it seem as if there was some kind of pre-process that started before the subjective experience of free choice that actually caused the subjective experience of free choice, which implies that the subjective experience of free choice was not free choice at all, but was actually driven by some underlying mechanical system. And you see that in these network models kind of implicitly, because in the mathematical code, you see this little buildup over here, and then this will spike, and then that will spike, and then this will spike. And because it's a continuous system, nothing is going to appear kind of out of nothing. There will be a continuous buildup towards something happening. You do also get discrete models of this, but I'm focusing on the continuous one. And so these kind of network models almost rely on this idea of something building up towards an action or a thought or an idea or some sort of cognitive behavior. And so I'd say that that's one of the key assumptions in these types of network models. Another type of model that also falls into the broader category of computational theory of the mind is information theory. The basic premise of this type of theory is that when we receive stimuli from our environment, there's so much stimuli that we don't really know what to do with it. And so to deal with the stimulus overload, we have a kind of inbuilt function or computing program in our brain that chooses a perception of that stimulus such that that perception minimizes the uncertainty. So you can imagine that given the same stimulus, maybe you get poked in the side, you could interpret that in any number of different ways, but the one that minimizes uncertainty is the one that your brain runs with. And so you seem less uncertain if you assume that the poke was a person than if it was a bear, given that you're in Auckland. And that sort of thing. And so this basic idea of minimizing uncertainty, that your brain is a computer and its primary role is to do this, both in interpreting or perceiving the external world, but also in decision making. Another type of mathematical model is Bayesian decision making. I suspect that anyone who's done any cognitive modeling has dealt a lot with Bayesian decision making. In this equation, I have probabilities. So whenever you see a P, that means the probability of something happening. A here is going to be the thing that's perceived. So A could be any number of things, and B is going to be a set of stimulus or stimuli. So for example, if I pick up my cup, then my eyes are receiving a set of stimuli from the cup. I'm feeling that it's warm through my fingers. And so there's a set B of stimuli that I receive from picking up the cup. What I then perceive is going to be what I decide A is through a computation in my brain. So I could decide that this is a cup of milk, a cup of coffee, not a cup at all, whatever it is. And the probability that I choose a cup of coffee, given the stimuli, which is this term on the left, is going to be equal to the probability that I'm actually receiving that stimuli, given that there is a cup of coffee, multiplied by the probability that there is a cup of coffee, divided by the probability that I receive that set of stimuli. So for now, I'm going to ignore these two and just focus on this red term here, because this is the one that attracts the most attention in this sort of modeling. I don't think I'm getting my name wrong. This is called the prior distribution. And this is what is learned in the model, in the brain, over time from when you're born to whenever. This is basically your expectation of reality. What is the probability that there is a cup of coffee? Given no stimuli, given nothing else, pure internal expectation. It has nothing to do with the external world. And so your brain is kind of performing two functions in this type of model. The first is to learn over time and build up a sense of expectation, which is given in this red probability here. And then the second is to actually make this kind of computation and then make a decision. The highest probability that you get on the left out of all possible A's is then the one you will go with in these types of models. Again, it's similar to the information one in the sense that whichever A gives you the highest probability is the one that minimizes uncertainty. Finally, we have one that I've come across a lot at this university, which is radical embodied cognition. So a lot of these kinds of models that I've been looking at treat the environment as some external thing that has an input into the internal brain computer. The brain then does some kind of calculation, and then there's an output, often as a motor response, or perhaps as a particular perception of something, or perhaps as a decision, whatever the appropriate response is. Radical embodied cognition places a real emphasis on the environment not being an external thing, but placing us within that environment, within our body, and interacting with the environment. So it's not particularly different. I have some questions about radical embodied cognition, but there's a greater emphasis on the interaction between the person and the environment as things happen in time. So in this first type of model, the input will come in at the beginning, and then there won't be any other feedback from the environment as the computation unfolds. Where in the second type of model, typically there will be interaction with the environment in continuous time as the computation unfolds. And so the environment is changing as the person is acting or perceiving or whatever. And so this obviously comes with a slightly different set of assumptions as to how you approach these types of models. Anthony Chimero, who has a book called Radical Embodied Cognitive Science, but also a paper, says the meaning of thoughts and sentences is a matter of the relationship between thinkers or speakers and information in their environments. So everything becomes part of that relationship, that interplay between the environment and the thinker. These types of models are obviously very commonly used in neuroscience and by mathematicians, and they lead they've proven to be very powerful in explaining a wide range of things. And they lead certain thinkers like Sam Harris in his book Free Will to say, thoughts and intentions emerge from background causes of which we are unaware and over which we exert no conscious control. This is very much tied into that kind of Lubet's experiment idea, where there's some underlying process that's running, and then something appears out of that which we subjectively experience. And that's how these models work. There's an input, the brain does some computation, and then there's an output. And it's reasonable to assume that the only thing we're aware of is the output, the actual response. And like I said, these models have been incredibly powerful, by and large more powerful than the forebearers of those types of models. When you read the original literature, most of them were, oh, we'll try this, probably won't work. And most of them are quite shocked at how powerful these types of things have proven to be. So these types of models are often called brain-to-mind models, or upward causation, or bottom-up models. The basic idea that the mind, the subjective conscious experience, is being dictated to and controlled from the bottom, from the brain, from the mechanics upwards. A neuroscientist called Brooks says, the bulkiest parts of intelligence, perception, action, motor control, and coordination have been explained by these models. There have been few attempts to see how they fare with less bulky parts of intelligence, such as planning, decision-making, and attention. So there are some limitations. They haven't been able to explain everything, but they have been able to help us a lot to understand perception, action, motor control, coordination. Attention is one that I'm particularly interested in. For example, if you're asked to focus your attention on a particular aspect of an image, a different region of your brain will fire than if you're asked to focus your attention on a different aspect of that image. In that sense, the input or the stimulus is the same. It's the same image. And so from a purely mathematical perspective, you'd say, well, with the same input, you would expect the same output. And yet the role of attention is changing the areas of activation that you can observe in an MRI. As a critique of, say, the Lubet's experiment, the subjects are kind of free to wave their finger or wiggle their finger whenever they want to, but they're kind of not really free to not wiggle their finger at all, or to wiggle their finger uncontrollably, because if you go to an experiment and then the experimenter says, wiggle your finger randomly whenever you feel like it, you're not going to just go or not do anything, right? You're going to perform, you're going to have some expectation of what the experimenter wants from you, and you're going to act accordingly. And so there might not be, they might not actually be free, and perhaps that electrical buildup towards conscious experience of choice is not free, not random. And finally, the most important critique of these types of models is that we feel things, and the models don't account for that. This is a clip from one of my favorite movies called Ex Machina. See if I can get it to play. Okay, it doesn't look like it's going to play, but that's okay. In this scene, there's a human given by the man on the right speaking to a robot, who's the woman on the left, and he's telling her about Mary in the black and white room. And it's a thought experiment where there's a scientist who knows everything there is to know about color, the wavelengths, the amplitudes, the frequencies, what you can do with them, how you mix them, whatever. They've studied color their whole lives, but they live in a black and white room where they've never actually seen color. And one day they're allowed to go outside and they see color for the first time, and they have a totally new experience, a totally new realization. And the idea is that while they're in the black and white room, they are their brain, they are the computer. They can understand and process from input to output everything there is to know about color, but they don't know what it is to feel, what it's like to see the color blue or red or whatever. So we then come to the final type of model that I'm going to look at as a category, which is, are there then mind-to-brain models or top-down models that don't rely on the brain having some mechanism leading up to a conscious experience, but actually accommodate the conscious experience and see if that filters down into brain activity? And this would accommodate something like attention, where depending on what you're choosing, freely choosing to focus your attention on, will affect the activation levels in your brain. And I'm going to focus on two types of models that I've seen here. The first, and there are quite a lot. I can recommend the book if anyone's interested, that has many, many different proposals. The first is called fusion or integration. The idea here is that in Sam Harris's kind of quote, he used the word emergent. And the idea is that you can have a lot of simple mechanisms, and from that, you can have a complex behavior appear. So in the case of the brain, this would be a lot of simple interactions between neurons that lead to an emergent property of consciousness. Another way to think about this might be the behavior of ants in a colony. Each ant only performs a very simple function. One ant might find food, another ant might pick up food, another ant might move stuff to the nursery. And yet, as a colony, there emerges quite a complex social hierarchy, quite complex structures. The ant colony is designed in a very particular way. And so you can have these complex properties emerge from simple processes. But in the idea of emergent, each ant or each neuron remains a neuron even as the emergent property appears. The idea behind fusion or integration is that the new emergent thing is a brand new thing. And so within the ant colony, as it were, each ant loses all its individual characteristics. It's no longer an ant. You just have an ant colony. And it's not made up of ants. It's an ant colony. And in the model, there can be ants, but they are not part of the ant colony in some sense. In terms of cognitive models, what you would have then is neurons. From there, where you'd normally say consciousness might emerge, you just say consciousness is its own thing. It might come from this, but each of the neurons loses their individual characteristics or properties or behaviors in the context of this greater whole. And so it's not the whole is greater than the sum of its parts, it's that the whole is a brand new thing apart from the sum of its parts. And that this type of model obviously allows you to include basically anything you would like to. And finally, one that's received really a lot of attention, there's a lot of information out there on quantum models of the mind. They are, as a warning, mostly pretty difficult to understand. So to begin with, just from the kind of physical perspective, why would we care about quantum phenomena? Quantum phenomena usually are only relevant or applicable when you have a very small number of a very small particles. So when you're looking at something as large as the brain, quantum effects are usually completely irrelevant. Even if you're looking at something as large as a neuron, quantum effects are pretty much irrelevant. But there are particular things within neurons or within the flow of energy between neurons that are small enough for a lot of people to assume that there are quantum effects taking place. The two that I've come across is the one ion channel flows and the synaptic effects. Whatever that exactly means is quite small. So you're talking about a particular number of atoms or electrons flowing through where quantum effects might take place. And another popular one proposed by Roger Penrose and Hameroff are microtubules. Again, I don't actually know what that means and haven't really been able to understand it much from the papers I've read. But again, they're small enough for quantum effects to be important. If you then take quantum effects into consideration, it can completely change the way you move forward with these types of models. In particular, you get what I'm going to call the separation between the actor and the spectator as the same thing within these kind of quantum models. So I have on the screen a quote by Niels Bohr. He says, "For a parallel lesson in atomic theory, we must turn to the kinds of epistemological problems with which already thinkers like the Buddha and Lao Tzu have been confronted, when trying to harmonize our position as spectators and actors in the great drama of existence." The basic idea here is that when you have a quantum system, the very act of observing that quantum system changes that quantum system. From a mathematical perspective, what you normally have is a wave equation, the so-called wave equations, that's a solution to Schrodinger's equation. But whenever you look at it, it kind of folds into itself. And instead of being a wave function, you just get one particular aspect of it. And so the thing that you're observing is not the thing itself. If you take this idea of spectators and actors, where actors are the things that they're us, you know, we live in a world where quantum dynamics are real and take place, and so they're affecting us. And yet we're also spectators. So by the mere act of observing ourselves, we are causing that kind of quantum wave function to collapse into something new. And so we're both spectating reality, and yet we're part of it. And in the act of spectating, we're changing it. By taking this into account, you can, with a little nice bit of mathematical trickery, have both the spectator and actor in models of brain activity, which gives you a really kind of nice, and really, I mean, from a mathematical perspective, I think really elegant way of including the consciousness actually within the model. So it doesn't have to be separate. It can be included in the equations and in the model, and yet it can still be a free agent. And so these kinds of quantum models allow for things like consciousness and free will to be incorporated in the model and not just excluded either as an emergent property or something that is beyond understanding or mathematical description. So quantum physics informs us that there are mathematical models for brain activity which accommodate conscious thought, ignoring the stream of consciousness and brain activity, as is done by many neuroscientists, ignores the very thing that you're trying to study. In principle, quantum theory must be used and thus allow for the spectator to make choices which, as an actor, also affect the dynamics of the physical system. I'm going to stop there with the model and just have some reflections on some of the talks we heard yesterday. The first of which would be, when you're looking at a top-down model of cognitive behavior, you're having the consciousness dictate to the computer what sort of computations it's going to make and have an effect. But in a real, more realistic top-down model, there'd be something higher than the individual consciousness. And that would be the culture or the group within which they are situated. Because the culture or the group affects their particular expectations, their desires, and what they're willing to pay attention to. Where I think the reason attention has been focused on so much recently is because it's a very easy thing to measure. You can actually ask someone what they paid attention to, where asking someone what did you freely choose to do is a bit more tricky. The next idea that I think was interesting from Jamie's talk is that when you have fusion or integration of emergent properties into a new thing, so that's where you had the ant colony as a totally separate thing to the ants themselves. It seems similar to me in some ways to Sartre's idea that consciousness is continually being reborn. So you can have your brain as a mechanism, but the thing that seems to be emerging is fusing into a brand new consciousness at every moment in time. And finally, the idea of spectator in quantum models seems pretty analogous to the reflecting consciousness that Joshua spoke about yesterday, in the fact that what we observe consciously is not the thing itself. In the fact that we are observing it, the consciousness is reflective. In the case of the actors and the spectators, by being a spectator, you are changing the reality itself while remaining a part of it, while remaining an actor. And that's all from me. Time for questions.